So scheduler, there's a function known as schedule, which is the function which implements the scheduler. So this function is implemented in this file, kernel sched.c. So one of the most important data structure which is used by the scheduler for this function is run queue. So run queue is a data structure which contains the list of all the processes which are in task underscore running state. So schedule function uses a data structure known as run queue, and run queue is a data structure which contains all the processes which are ready to run or which are running. So each CPU has its own run queue, and each active process will be either present on one run queue. They will not be present on all the run queues. They will be present only on one run queue. So how is this scheduler invoked? Who calls this scheduler? So there are two ways. One is a direct way. When the current process which is executing, it does not have the resource which it needs and it wants to block itself until it acquires the resource, it calls schedule. The lazy way is when the process is running, and the time slice allocated for the process has expired, then the scheduler is invoked. So these are two ways where the scheduler can be invoked. Direct way, where the current process will itself call schedule. Lazy way, when the time slice of the process is completed. So why do we need sleeping? So most of the times processes has to wait for a certain event. For example, the events can be device initialization, or waiting for the IO to complete input and output operation, or waiting for a fixed interval of time to elapse. So these are the various events where the process needs to wait. If in such cases, the process is set to sleep on that event. So a process can go to a sleep when it calls schedule function. So when you call schedule, it is moved from the scheduler's run queue. So as we have said, all the processes which are running are present in the scheduler run queue. When you call schedule, the process is removed from the scheduler run queue until something comes which will make this event happen. The process will not be scheduled back on the CPU and will not be running. So if you call schedule, it will be removed from the processor, from the CPU's scheduler run queue, and it will not run until someone keeps the process back into the run queue and call the schedule again. So these are the various process states we have. One is a task underscore running. And this process is either running or it is waiting for the CPU to complete the existing process. It means it is ready to run. Task underscore zombie. Task has terminated and it is waiting for the parent to call wait. Task stopped. When you say control Z, it sends you a 6 stop signal. That is the state where it is in task under the process is in task underscore stopped state. Then we have task interruptible, task uninterruptible. So the difference between task interruptible and uninterruptible is task interruptible can handle signals. So when signal is sent to a process which is in task interruptible stage, it will wake up and become runnable. When the signal is sent to a process which is in task uninterruptible stage, it does not wake it up. So this is the major difference between task uninterruptible and interruptible. So if you send a signal to a task interruptible process, it becomes runnable. Means it will go into task underscore running stage. But for task underscore uninterruptible, the signals are being ignored by this particular state. So uninterruptible is mostly used by the device drivers which are waiting for disk or network input output to complete. So the device drivers which are waiting for disk IO or network IO mostly use uninterruptible state. So how to find out whether my process is in interruptible stage or uninterruptible stage, I can use ps command. So if I say ps hyphen l, it will give me state. So S means it is a sleeping stage. Whether it is a sleeping in interruptible or uninterruptible, we can see S means it is an interruptible sleep. D means it is an uninterruptible sleep. So task underscore uninterruptible is D. Task underscore interruptible is S. So here you can see we have bash as in uninterruptible sleep, right? S means interruptible sleep. And also you can see there's a field known as wchan, which means wait channel. This will tell you what is the kernel function in which the process is sleeping, means the system call which the process is waiting on. So bash is waiting on a system call known as wait. If you do el, ps-l will give you only the processes associated with the current shell. If I want to see the all the processes on the system, I can use el. So when I say el, I say less. You can see many of the processes are in interruptible sleep stage that can be interrupted, means signals can be delivered to the process. You can see this is the function, this is which it is waiting on. Wait channel is this tells the system call which this particular process is waiting on, and you can see it is in a interruptible sleep. Mostly they are waiting on a poll system call. You can see most of them are S. We do not see anything as D here. D is mainly used for disk IO or a network IO. S is interruptible sleep. This can be interrupted by the means signals can be delivered to this process and the process will become runnable from task underscore interruptible. So we have seen schedule function. We know schedule function invokes or calls scheduler, and it will pick up the next process or task from the run queue. We know run queue is a data structure which contains list of processes which are in task underscore running stage. And schedule, when you call schedule, scheduler will pick up the next task or process from the run queue. So here I'm printing the processor ID before calling schedule. I'm calling schedule. Then I'm printing the processor ID again after calling schedule. Let me run the dmessage thing. So I have dmessage running in background. I'm compiling the program. So you can see it has executed before schedule and after schedule. So this means the process was not in a sleeping stage. So you can see from the code, it executed this line and then it instantly executed this line. So this means you can see here the difference is very less. What do you think has happened here? Why is the process not sleeping here when I call schedule? Can you guess? Why is the process not sleeping here? So what will be the state of the process when it is executing this line? What is the state of the process when it is executing this line? We have different states. the state of the process when it is executing this line is task underscore running, right? It will be in task underscore running state. So when you call schedule with a task which is already in task underscore running stage, it will not be removing it from the run queue. It will again schedule it because this process is already in the run queue. This process is already in the task underscore running stage. So it will not make the process sleep or block. It will again schedule the process because it's already in the run queue. So process which is invoking the schedule will voluntarily yields the processor, but as the process is still in the run queue, it will be scheduled again. So it will yield the processor, but as the process is not removed from the run queue, it will be scheduled again. So you have to call set underscore current state before calling schedule. So you have to set the state of the process either in an uninterruptible stage or an interruptible stage before you move it from the run queue. So if you call set underscore current state before calling schedule, schedule will first move the process from the run queue and then it will yield the processor. So the header file for this is linux sched.h. So when the schedule function is called with the state as interruptible or uninterruptible, an additional step is performed. The currently executing process is moved from the run queue before another process is scheduled. So this effect of moving the currently executing process from the run queue is nothing but the executing process will go to sleep as it is not present on the run queue. Hence, it will not be scheduled by the scheduler. This is how a process can sleep. So to make a process sleep, you have to first set the state of the process either as an interruptible or uninterruptible and then call schedule. Normally, simply calling schedule will not work because it will be scheduled back again because the process is in the run queue. So we here call set the state of the process as interruptible and we call schedule. So you can see it has printed before schedule and now it is in the sleeping stage. Let's see. So what will be the value of state here, S or D? We have set the state as interruptible. So what does PS will show now for this particular state, S or D? It will show S because it is in a interruptible sleep. If I do an uninterruptible sleep there, this will show a D. So how long do you think the process will be in a sleeping stage? How long this process will be in the blocking stage or a sleeping stage? So we have removed the process from the run queue. So how long this process will be in a blocking stage or a sleeping stage? Can anyone guess?
Until signal come.
Until signal is delivered to the process. Yeah, that's a perfect answer. So until, as we have set an interruptible thing, until we send a signal, suppose control C is a int, it will be until that time it will be in a sleeping stage. So when we send a signal, what happens is task interruptible will become task running. It will be moved to the run queue and then schedule will work. And the CPU will assign, the scheduler will assign the CPU to the process and this line will execute. So, but if I do not pass any signal, then there is no one which is trying to wake up the process, and the process will be sleeping unconditionally. So if I do not send a signal like control C, control Z, the process will be always in a sleeping stage because there is no one to wake up the process. So to wake up a process, we have a separate API known as wake underscore up underscore process. So if you have a task structure which is struct task underscore struct, you can pass the address of it to this function wake underscore up underscore process. And the implementation for this is in this file sketcode.c. So it is in kernel sketcode.c. So what this function does is it will set the state to task underscore running, and it will put the task back on the run queue. And the scheduler will run this process only when it gets time for the next process. So if the return value for this function is 1, the process was all. So if you have a process, this is already running, and if you call wake underscore up underscore process, it will return 1. If you have a process which is blocked or in a sleeping stage, and you call wake underscore up underscore process, it will return 0. So I have a character driver, basic character driver, which has open, read, write, release implemented. In the read, what I do is I set the process state as, so let's say we do it in uninterruptible. I set the process stage as uninterruptible. And what I'm doing is I have created a variable for storing the reference of a sleeping process or sleeping task. So I have a pointer of task underscore struct, a global pointer, and I am assigning the current, storing the value of current process into this. And then I'm calling schedule. In the read function, when our user calls read, I'm doing this operation. I first set the state as uninterruptible. So whenever someone calls schedule, the process will be moved from the run queue and the process will be blocked. In the write function, as I am storing the task here, I can use it in the write function. So I'm calling wake underscore up underscore process, which will set the task state as running and move back place the task into run queue. So let's see now what happens. So I do a cat, which will call my read function. So what will be the value of state here when I do ps-el on the cat?
D.
D, because it is a uninterruptible stage. So it will be D. S is for interruptible, D is for uninterruptible. So now it is waiting, it is blocked until someone calls wake underscore up underscore process, which we are doing it in our write function. And you can see before schedule and after schedule. So this is how you can implement. This is the basic of blocking in Linux kernel. You have a schedule function and you have a wake underscore up underscore process function, and you need a task underscore struct to be stored for the wake underscore up underscore process to call wake up the sleeping process. So basic of sleeping in Linux kernel: schedule and set current state. We have seen 3 APIs: set current state, schedule, and wake underscore up underscore process. So as we have seen schedule, there is one more function known as schedule underscore timeout. So I want to wait for a few seconds. If and this function can be used like if you want the process to do not block in like infinity. If I do not receive a wake underscore up underscore process for a particular timeout, I have to return from that particular function. I do not want it to run infinity time, like all the time. Or so with schedule underscore timeout, with schedule you have a problem until someone calls wake underscore up underscore process, it will be running there. It will never come out from the schedule function. So with schedule underscore timeout, you can give a timeout. The timeout value is in jiffies. Jiffies will be doing in our upcoming sessions. So we'll give the value of jiffies and it will wait to make the current task sleep until timeout jiffies have elapsed. And the return value is 0 when the timer, when whatever the jiffy value you have given has expired, or if the wake underscore up underscore process has been called before this timer has expired or before the jiffies has elapsed, it will give the remaining time, whatever it has, whatever the remaining time in jiffies is available as a return value. So schedule underscore timeout will not wait indefinitely. It will, whatever the time you give as an argument, it will wait until that time. If a wake underscore up underscore process is called before the timeout, it will return the value, the remaining time in jiffies. So head z is nothing but the value of jiffy in 1 second. So when you say 10 into head z, we'll be looking head z in our upcoming sessions. But for now, you can think of head z as the amount of jiffies for 1 second. So here we are scheduling for 10 seconds. So we are saying go for 10 seconds. And if I do not receive a wake underscore up underscore process, then come out of this function and return me a 0. So I'm setting the state as uninterruptible, and I'm setting this the same code, and extra I'm printing the value of schedule underscore timeout here, and I'm calling wake underscore up underscore process here. Call cat, and I call echo here. You can see the return value is the remaining time which was not finished in jiffies. So this is the remaining jiffies. So and if available, like we have given like some amount, and whatever the amount which is it is not completed, the timer has not expired, is this. So if I do not call wake underscore up underscore process using echo, I get a return value as 0 after like 10 seconds because I said 10 into hz. So you can see 95, 195 and 206, and the return value is 0. So here I'm doing a condition check. The same code, but I'm doing a condition check. What I'm doing is I'm checking whether I have received 20 bytes. So whether the user is entering 20 bytes as using write command or the write system call. So only when I receive a write of 20 bytes, I come out of the read function. Otherwise, I will be continuously sleeping in the block state. So I have a do while which is checking whether the write count, which is a global value which I'm setting in the write function, and I'm checking whether the write count is less than 20 or not. If it is a less than 20, then I'm again going back to a sleeping stage by calling schedule. So let's see what happens now. So here in the we have added additional code where we are just checking whether the write count is less than 20 or not. So I call cat here again. Now I'm in a interruptible sleep, which can be interrupted by, but you can see now I have sent a signal and I'm not handling that signal. So you can see it is continuously calling schedule. So let's say echo hello, and you can see as the logic is not properly handled, how it behaves. So when I have sent 20 bytes, it came out from the schedule, and it has come out of the do while loop, and it has executed the read function. So you have to handle, we are not handling the signals here in the code. You can see we were not handling the signals, whether we have received a signal or not. So this is the reason when I send a control C, it went into a do while loop, continuously calling schedule, schedule, schedule. So again, I'm running this. Suppose if I send only 5 bytes, it will again call schedule. If I send 21 bytes, which is greater than 20, the read function is completed. So till now we have seen how to keep only one process into a sleeping stage. So the previous code, what we have seen is only for the one process, because we have only a global variable as to store only a reference of one process. If I call from two shells, cat, cat, one of them will be lost because we are updating a global variable. So like to avoid this, what we'll do is we'll create a linked list. So we'll create a task queue where we'll be storing whatever the task, each and every task pointer into this task queue. So I have a list underscore head. I have this structure for this. I'm creating a head node here. And whenever someone calls read, I see whether write is available. So initially the value of write available is false. As write is not available, it will come here. We'll create a structure of this. It will fill the current. It will add it into the linked list. And it will set the current state as interruptible, and it will call schedule. Whenever someone calls read again the new task struct will be added into the linked list. In the write function, I check whether the list is empty or not. If the list is not empty, I pop out, remove the first node by calling list entry. I get the pointer. So this will do internally container off, and I delete it. I delete the linked list node, and I call wake underscore up underscore process. This is how I can implement a task queue. So I'm implementing a task queue for multiple processes. Previously, we have seen only for one process because we were only having a global variable. But here we have implemented a linked list of processes which are waiting for the resource. So I'm calling cat here. This is now blocked. I call cat again. This is also blocked. Now when I call echo here, which process do you think will be unblocked first? We have two processes which are blocked. Now if I call echo here, which process do you think will be unblocked? So we are using linked list, and we are using list add tail. So list add tail will add the node to the end of the list, and then we are using list entry to get the first node, and then we are deleting it. So let's see. So this has gone because this was the first node in the linked list, and this is still waiting. Call it again, and this is also completed. So this is how we can implement. We can keep multiple processes to block until the resource is available or not. So there's a problem something known as lost wake up problem. So we have seen processes, they're going to sleep, or sleep here means calling schedule, after checking the condition. So condition here is whether write is available or not, the user has called write or not. So processes, they go to sleep after they call, after they check some condition. So lost wake up problem arises out of a race condition that occurs while a process goes to a conditional sleep. So this problem happens due to a race condition when the process goes to a conditional sleep, which is this. We have seen till now the conditional sleep. So suppose you have a process A, which is checking whether the linked list is empty or not. So if the linked list is empty, it calls set current state as interruptible and it calls schedule. And then once the process is woken up, it will perform operation on the linked list. The second process comes, which will add a node to the linked list head, and then it will wake up the process A. So do you think is there any problem in this code? So you have two processes. One process which checks whether the linked list is empty. If it is empty, it calls sets the state as interruptible and will call schedule. The second process comes, it will add a node in the linked list and it will call wake up process. So do you think is there any problem in this code? Is there any problem which happens when these two processes are running concurrently on two CPUs?
Process A do not know that process B added a data.
So like what happens when at what line? So process A is executing this line, right? And process B is executing this line. If process A has executed this line and it has found the linked list to empty, it comes inside the if loop. And suppose the process A time slice has completed. The time slice which was allocated for process A has completed. So it is not running on the CPU. So when it comes back, it will start again here. Now process B comes, it will call add a node, list add tail, it will call wake up process, and the process will because the process is already in the run queue, this will not work. Wake up process, when the process is in run queue, will not do anything. This process will again come out. It calls, sets the state as interruptible, and it will go to the blocking stage. So this process is going to the blocking stage even when there is a node added to the linked list. So even it is having a node in the linked list, it is going to the sleeping stage. So it has lost this particular wake up. So it has lost this wake up. So process A has lost the wake up, and this is known as lost wake up problem. So process A is sleeping even though there are nodes available on the list. So what is the solution for this problem? Is there any solution for this problem? How to avoid this condition? I do not want my wake up to lost. Can I change the code such that this problem is gone? Is there any way, like if I modify this particular 4 lines or 3 lines of code, so I can avoid the lost wake up problem? Think of a solution here.
Locking mechanism.
Yeah, locking mechanism is can I use locking mechanisms when I am sleeping? So can I use spin locks here? Can I acquire a spin lock when I'm going to sleep? Uh, So I can use semaphores. I can use mutexes. Yeah, I can use mutexes because I can sleep while holding a mutex, but I cannot sleep while holding a spin lock because schedule will put my process into sleep stage or blocking stage. So we can use locks to avoid this problem. So we will acquire a lock before modifying this particular thing. But there's a better solution without using lock for this. So let's look into the solution here. So problem goes if we modify our code. So if I set my state of the process here, like I set the process state as task underscore interruptible, and then I check the condition, and then if I have elapsed my timer, and then it comes and it says wake up process, and I'm here. What happens is the problem goes away. How the problem goes away? So whenever wake up underscore process is called on a process whose state is interruptible or uninterruptible, and the process has not yet called schedule, it changes the state of the process to running. So you are here, your state of the process is interruptible, and you call wake underscore up underscore process, it becomes the state of the process becomes task running. What happens when I call a schedule with task underscore running? Will it be blocked? If I call my process with the state as task underscore running, will my process be blocked? We have seen that, right? The process will not be blocked if the state of the process is task underscore running. So this problem can be solved if I first set the state as interruptible, and then I check the list, and even if my timer has time quantum or time slice has elapsed, and it came and it called wake up underscore process, it will change the process state back to running. And if you call schedule with a process which is running, will not work. It will again run the process, and it will come back and it will check the list is empty or not. As the list is not empty, it will execute the rest of the code. So we have solved the problem of lost wake up by just setting the state first and then checking the condition. So we have to first set the state of the process and then check the condition. So this is a snippet from the file kernel kthread.c. Do you think, is there any problem in this code here? Is it free of lost wake up problem? Is it free of the problem which we have discussed? It's free, right? Because we are first setting the state and then we are checking the condition, and then only we are calling schedule. So why are we doing this additional thing? Why do you think this particular line is needed? Setting the state of the process as running. We are setting the state as interruptible. If the list is empty, we schedule the process, which will move it from the run queue. And someone calls wake up, the process will be back in a running stage. Why is this needed? Any guess? So you're setting the state of the process as interruptible. What happens? So let me take you to the code. I have the code here. So this is a file, set current state. So this is the code here, which we are seeing. This first setting the state, and then this doing all those. So what is, why is this needed? So what happens when the list is not empty? So here we are thinking of a condition where the list is empty. But if the list is not empty, it will not go inside the schedule. And the state will be, if you do not do this, the state will be on a interruptible stage. So to avoid that, we have to set it back to running. Because the list is not empty, schedule will not be called, and we have to manually set it back to the running stage. So what we are doing is, we first call interruptible, and if the condition is failed, we are setting it back to running. So any questions in this? Schedule, set current state, and wake underscore up underscore process. So let's look into sleeping thing. So sometimes a process may need to go to sleep for a particular amount of time. Like for some milliseconds, my process wants to go to sleep. So I know my device initialization will take 100 milliseconds. So I only want to sleep for 100 milliseconds, and I want to wake it up back after 100 milliseconds. So kernel provides APIs, which we have seen till now, msleep. The header file for this is delay.h. So it will sleep for that particular milliseconds. So the code is very simple. It has added the header file. It is going to sleep for 1 second. So not 1 second, it's 1 minute. I'm calling msleep, and it's going to sleep for 1 minute. So it has started the 1 minute sleep. What do you think? Now I want to find out whether the process is in a interruptible sleep or uninterruptible sleep. Let's see how I can do that. ps-el ns-mod. What is this? Interruptible or uninterruptible?
Uninterrupted.
It's uninterruptible because it's D here. So an msleep will put the process in an uninterruptible sleep. So I cannot send a signal, nothing happens because signals are ignored or not delivered to the process when it is in an uninterruptible sleep. So once it has completed 1 minute, it has come back. So there's another function. If you want msleep as an interruptible sleep, if you do not want an uninterruptible sleep, I want interruptible sleep, I can use msleep underscore interruptible. It will put my process into interruptible sleep. And you can see it has a return value as unsigned long. Normally it is 0, but if the process has received a signal, then the return value is number of milliseconds remaining in the original requested sleep period. So if it receives a signal before the sleep has completed, the return value is number of milliseconds remaining. So let's see this example. So it has started 30-second sleep. Let's see the value of PS, and it is S. S means it is an interruptible sleep. And if let's wait for 30 seconds to see whether the return value is 0. 0 means it has completed its 30 seconds sleep. So it has the return value is 0 because it was not interrupted while it was sleeping. So let's run it again. Now when I says Control C, it has given us the remaining milliseconds available of the original requested sleep because it has received a signal. The return value is not 0, it will be the remaining milliseconds. So if I want to sleep in seconds, I have a separate function. Till now we have seen uh, M sleep, which is millisecond sleep. If I want sleep in seconds, I have S sleep. So I have given a 10-second sleep. Let's give us more. Let's give me 30 seconds. And let's verify whether it is in an interruptible or uninterruptible. And S sleep is uninterruptible sleep because it has, we are not giving underscore interruptible there. And we do not have for S sleep as S sleep uninterruptible, not interruptible. We only have for S sleep as task underscore uninterruptible. We do not have task interruptible for S sleep. We have it for M sleep, but we do not have it for S sleep. Kernel do not provide an API for that. So we have seen M sleep and S sleep. So how do you think these are implemented internally? What is the
In timers.
using timers? Yeah, internally it is timers. But whatever APIs which we have seen till now, using those APIs, are they implemented?
No.
We have seen schedule underscore timeout. We have seen wake underscore up underscore process. We have seen set current state. Do you think are they implemented using this? So let's see whether they are implemented using this or not. So implementation for them is present in kernel timer.c as we have said, they are implemented using timers. Let's go into the kernel timer.c and let's look for msleep. So msleep, what it is doing is it is first converting the milliseconds into jiffies and it is calling schedule timeout uninterruptible. So it is internally using schedule timeout msleep uninterruptible. Let's look into msleep interruptible. It is using schedule timeout interruptible and then it is returning whatever the value. Schedule timeout interruptible will give us the value in jiffies. The jiffies value is converted to milliseconds and given back to the user. So what about S sleep then? S sleep is not implemented here. So let's S sleep is implemented in delay.h file. So you can see S sleep is very simple implementation. It's an inline implement. They have declared it as an inline, and you can see it is internally calling msleep seconds into 1000. So very simple implementation of sleep. They are internally using msleep. So we have seen all of them are using schedule underscore timeout as a API. And you can see schedule underscore timeout is here again, which is using a timer. As we have said, it is using a timer. It is yes, it is using a timer. They have used a timer there. They have set up a timer and they are calling schedule. So they are using a timer for schedule timeout. Including a timer, they are using the schedule APIs which we have seen till now. So you have any questions till now which we have discussed? So let's revise what we have done.
Run queue.
Yes.
Yes.
Yes, we need to call, otherwise the process will not be removed in the run queue.
Backup process. Yes.
Okay, that's all for this, what we have seen today.